620 light-years from here, in the constellation Chamaeleon, there is a planet with no sun. It does not orbit anything. It never has, as far as anyone can tell. It is simply falling through the dark, alone, at 5 to 10 times the mass of Jupiter. And right now, it is eating. 6 billion tons of gas and dust are falling onto its surface every second. Not per year, per second. That is the mass of Mount Everest disappearing into a starless world roughly every 2 minutes. It is about 1,000 Great Pyramids per second. At that rate, it would swallow every drop of water in Earth's oceans in under a decade. And nobody expected a rogue planet to be doing anything like this. Planets are supposed to be the quiet objects, the passengers, the things that get pulled around by stars, not the things that behave like them. This one is feeding through a magnetic field, the way a newborn star does, and it brightened by a factor of several while astronomers watched. Stick around, because I'm about to walk you through what scientists actually just confirmed about this object, what the James Webb Space Telescope saw when it looked directly at it, and the part of the result that still has no accepted explanation. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration. Let's go back to where this story actually begins. The object has a name that nobody enjoys saying out loud. CHA110-70768-7626326. In the papers it gets shortened to CHA-1107. It was first catalogued in 2008 in the Chamaeleon star-forming complex. At the time, it was one entry among many in a survey of faint, cool, red things. It was not a headline, it was a data point. What made it slightly interesting, even then, was that it showed signs of accretion. Accretion is a plain word for a plain process. Material falling inward and landing on a surface. Young stars do it. Baby planets do it. A free-floating object with no star should, in principle, have run out of anything to fall on it long ago. CHA-1107-7626 had not. Skip forward to the first half of 2025. An astronomer named Victor Almendros Abad at the Astronomical Observatory of Palermo, part of Italy's National Institute for Astrophysics, started a monitoring campaign on this object. I want you to understand how unglamorous that work is. A monitoring campaign is not a discovery. It is a schedule. You point an instrument at the same faint smudge, over and over, on whatever nights the telescope gives you, and you write down how bright it is and what its light is made of. Most of the time, nothing changes. The value of the work is that you build a baseline, a boring, reliable record of normal, so that if something abnormal happens, you can prove it. He used the X-shooter spectrograph on the European Southern Observatory's Very Large Telescope in Chile. A spectrograph does one job. It spreads incoming light out into its individual colors. Hot gas falling onto a surface leaves fingerprints in those colors. Hydrogen, in particular. If you can read the hydrogen lines, you can estimate how much material is landing and how fast it is moving when it hits. April, May, quiet, normal. Baseline. Then, in late June 2025, the baseline broke. The object got brighter, not subtly. It climbed by roughly 1.5 to 2 magnitudes, which in plain terms means it became about 3 to 6 times brighter in visible light. The hydrogen lines broadened and intensified, which means material was falling in faster and harder. By August 2025, the team measured the accretion rate at approximately 6 billion tons per second. That was around 8 times higher than the object's quiet state rate. The research was published in the Astrophysical Journal Letters, and the European Southern Observatory announced it on October 2, 2025. The co-author list includes Ray Jayawardena at Johns Hopkins University and Alex Schultz and Belinda Damian at the University of St. Andrews, names that come up repeatedly in this field, and that will come up again later in this script. Almendros Abad's summary of the measurement was direct. This is the strongest accretion episode ever recorded for a planetary mass object. Not the strongest for a rogue planet. The strongest for any object in the planetary mass range, anywhere, ever measured. That is the turning point. An object that was a footnote in a 2008 catalog became, in a single season, the clearest evidence yet that the line between planet and star is not a line at all. So how does a planet with no sun eat 6 billion tons a second? The chain is short, and every link in it has been observed somewhere before, just never all together on something this small. Step 1. CHA-1107, 7626, is young. The estimates put it at roughly 1 to 2 million years old. On a cosmic clock, that is an infant. Our own solar system is about 4.5 billion years old. This object has existed for less time than modern humans have. Step 2. Because it is that young, it still has leftovers. It is surrounded by a disk of gas and dust, a flat, rotating pancake of material that never got incorporated into the object itself. The James Webb Space Telescope measured what that disk is made of. It found silicates, which is the mineral family that makes up most of the rock under your feet, showing the characteristic silicate signature near 10 microns in the infrared. It also found hydrocarbons, carbon-based molecules, rock dust and soot, essentially, in a ring around a starless world. Step 3. That disk does not simply hover there. Material at the inner edge loses energy and drifts inward. Step 4. This is where it stops behaving like a planet. The object appears to have a magnetic field, and the evidence points to that field controlling the final stage of the fall. Instead of the gas spiraling gently down onto the equator, the magnetic field grabs the ionized material at the inner edge of the disk and channels it along field lines, funneling it down onto the surface in concentrated streams. Step 5. Those streams do not land gently. They hit at high speed and turn their motion into heat. The impact points become hot spots, patches on the surface that are dramatically hotter and brighter than the rest of the object. That is what you are seeing when the brightness jumps. That is the entire mechanism. Disk, drift, magnetic funnel, hotspot, light. And here is why it matters. That exact sequence, magnetically funneled accretion, producing hotspots, is textbook young star behavior. It is how astronomers describe the growth of a newborn sun. It has been observed in stars and in brown dwarfs, which are the in-between objects too heavy to be planets and too light to fuse hydrogen properly. It had not been observed in something at 5 to 10 Jupiter masses. For scale, Jupiter is about 318 times the mass of Earth. So this object is somewhere between roughly 1,600 and 3,200 Earths. That sounds enormous. In stellar terms, it is nothing. It is far too light to ever ignite hydrogen fusion. It will never be a star. It cannot be. And yet it is growing like one. Now I want to be honest with you about how hard this measurement is, because the difficulty is part of the result. Start with the distance. 620 light-years. Light from this object has been traveling for 6 centuries. What the Very Large Telescope collected in 2025 left Cha 11107-7626 around the year 1405. Everything in this story, the burst, the brightening, the hotspots, already happened 620 years ago, and the news is only arriving now. There is no way to shorten that. There is no follow-up mission. Nothing built by humans is going there, and nothing will, on any timescale worth discussing. Every fact in this script had to be extracted from photons. Second constraint. It produces no light of its own worth speaking of. This is not a star. There is no fusion furnace. Almost everything it radiates is leftover heat from its own formation, plus whatever the accretion adds. It glows in the infrared, faintly. And infrared is exactly the part of the spectrum that Earth's atmosphere is worst at letting through. Third constraint. It is embedded in a star-forming region. The Chamaeleon complex is full of gas and dust. Dust reddens and dims everything behind it. So before you can measure anything, you have to estimate how much light the intervening dust ate and correct for it. That correction is a source of uncertainty in every number I've given you, and the researchers say so plainly. Fourth constraint, and this is the one that nearly killed the whole result: timing. An accretion burst is an event. It has a beginning and an end. If your telescope time falls in the wrong months, you see nothing. Almendros Abad's team happened to be running a scheduled campaign when this thing lit up. That is not skill. That is a campaign design that assumed nothing interesting would happen, colliding with something interesting happening. And they still would not have known whether it was a one-off. Except for one thing. They went back into the archives. They pulled older observations, including data from Sinfoni, an earlier instrument on the Very Large Telescope. And in that archival record, they found signs that Cha 1107-7626 had done this before, around 2016. That changes the meaning of the 2025 event completely. One burst is an anomaly. 2 bursts is a behavior. It suggests these episodes recur, on a timescale that is currently unknown, which puts this object in the same category as a class of variable young stars that flare up repeatedly as their disks feed them in pulses. 620 light-years, 5 to 10 Jupiter masses, 6 billion tons per second, 8 times its own baseline. Those 4 numbers are the whole story, and every one of them had to be reconstructed from faint infrared light that left before the printing press. Let's take the finding apart properly. Between April and May of 2025, the object sat at its quiet rate. Then, from late June through August, the accretion rate climbed to roughly 6 billion tons per second, about 10 to the -7 Jupiter masses per year, in the units the paper actually uses. Here is what the data looked like across different wavelengths, because this detail is what convinced people. In visible light, the object brightened by roughly a factor of 3 to 6. In the near-infrared, it barely changed at all. In the mid-infrared, it went up slightly, a modest increase, on the order of 10 to 20%. That uneven pattern is the fingerprint. If the whole object had simply gotten hotter, everything would have brightened together. Instead, the visible light spiked because small, extremely hot spots were dumping energy at short wavelengths, while the bulk of the object, the part that dominates the near-infrared, stayed almost exactly as it was. The mid-infrared crept up later, because the inner edge of the disk absorbed some of that new energy and warmed. That is not a coincidence. That is a mechanism showing its work across 3 separate parts of the spectrum, in the pattern the model predicts. Why it contradicts expectations. Nothing in the standard picture of planet formation requires a free-floating, 5 to 10 Jupiter object to still be actively feeding, let alone feeding in violent pulses, at magnitudes that would look at home on a newborn star. What remains unexplained? Nobody can currently say what triggers the burst. In young stars, several candidate mechanisms are proposed: instabilities in the disk, gravitational disturbances, clumps of material arriving at the inner edge. Which of those applies to an object this small is an open question. Researchers cannot yet fully explain the trigger. The Very Large Telescope caught the burst. The James Webb Space Telescope explained the setting. Webb observed Cha 1107, 7 to 626, with 2 instruments: NIRSPEC, which handles the near-infrared spectrum, and MIRI, which handles the mid-infrared. Together, they cover the wavelengths where cold dust and warm molecules give themselves away. What they found: an excess of infrared light from roughly 4 to 12 microns. Excess means more infrared than the object itself should produce. That extra light is the disk, dust, warmed, glowing. Inside that excess, the silicate feature near 10 microns. Silicates are the raw material of rocky worlds. The same feature shows up in the disks of young stars and brown dwarfs. Alongside it, hydrocarbon emission, a carbon-rich chemistry, in a ring around a world with no sun. And during the burst, Webb registered changes. There was a tentative signature of water vapor, and a slight shift in the carbon signals, which suggests the extra heat from the accretion event was altering the chemistry of the inner disk in real time. The dust signature itself, meanwhile, stayed essentially the same. Sit with that for a second. This is a starless object, 620 light-years away, 5 to 10 Jupiter masses, and we have a chemical inventory of the ring of debris around it, plus evidence that its chemistry changed while we were watching. Why it contradicts the older model? For a long time, disks were understood as a feature of star formation, something a star has while it builds planets. Finding rich, chemically active, mineral-bearing disks around objects at planetary mass means the machinery of system building does not require a star at all. What remains unexplained? Whether that machinery ever finishes the job. Nobody has confirmed a moon or a ring around any free-floating planetary mass object. The ingredients are there. The outcome is unobserved. Cha 1107-7626 is not a freak. It is the loudest member of a group that keeps growing. The first free-floating planetary mass objects were reported in the year 2000 by 2 independent teams, one working in the Sigma Orionis cluster, one in the Orion Nebula cluster, using infrared telescopes, including the United Kingdom Infrared Telescope in Hawaii. Objects below the mass where deuterium burns, drifting with no star attached. In 2023, Webb turned its imaging on the Orion Nebula, and the count exploded. The survey identified on the order of 540 candidate planetary mass objects in one region, and roughly 80 of them appeared to be paired, about 40 binary systems, two Jupiter mass objects orbiting each other with no star anywhere in the arrangement. The researchers, Samuel Pearson and Mark Makarian, named them JUMBOs, Jupiter Mass Binary Objects. In 2024, a team including Alex Scholz, Koralka Mujic, Adam Langeveld, and Ray Jayawardhana used Webb's NIRISS instrument for a deep spectroscopic survey of NGC 1333, a young cluster about 960 light-years away in the Perseus molecular cloud. They found 6 new planetary mass candidates in the range of roughly 5 to 15 Jupiter masses. One of them, near 5 Jupiter masses, showed an infrared excess, a disk. At the time, it was the lowest mass object known with 1. That survey produced a second result that gets less attention and matters more. Webb was sensitive enough to detect objects below about 4 Jupiter masses in that cluster. It did not find any. Why that contradicts expectations? If these objects were mostly giant planets ejected from ordinary solar systems, you would expect the population to keep going down in mass. It doesn't. There appears to be a floor. That floor is the strongest evidence yet that these things are not ejected planets at all. They are the smallest objects a gas cloud can collapse into on its own. The bottom of star formation, not the top of planet formation. What remains unexplained? How the pairs form. 40 binary systems of Jupiter mass objects should not survive ejection. A violent enough kick to throw 2 planets out of a system should not leave them gently orbiting each other afterward. At least one proposed formation route has been argued against in follow-up work. There is no accepted explanation. Here is where the science runs into language. The International Astronomical Union's definition of a planet requires that the object orbits the Sun, and by extension, in common usage, that a planet orbits a star. CHA 1107-7626 orbits nothing. By the strict definition, it is not a planet. But it is not a star either. At 5 to 10 Jupiter masses, it can never fuse hydrogen, and it is at the very bottom edge of the brown dwarf range, which is usually reserved for objects heavy enough to fuse deuterium, above roughly 13 Jupiter masses. So what is it? The paper's own co-author, Alex Scholz, has framed the open question directly. Are these the lowest mass objects that form like stars, or are they giant planets ejected from the systems where they were born? The CHA 1107-7626 result pushes toward the first answer. Magnetic funneling, hotspots, recurring accretion bursts, a mineral-rich disk. That is a star's biography, playing out in a body 1,000th of the Sun's mass. Why this matters beyond vocabulary? The categories were built from our own solar system. 8 planets, 1 star, tidy hierarchy. The galaxy did not agree to that arrangement. What Webb keeps finding is a continuum, where the same physical process runs from objects hundreds of times the Sun's mass down to objects a few times Jupiter's, and the labels we invented sit awkwardly across it. What remains unexplained? Where the boundary actually is, or whether one exists at all. The last number is the one that changes the scale of everything above. Estimates for the number of free-floating planetary mass objects in the Milky Way run into the trillions. Some published estimates put the figure at several trillion. Some analyses suggest they may outnumber the stars. I want to be careful here, because this is where space content usually goes off the rails. Those numbers are extrapolations. They come from counting objects in a handful of surveyed regions and scaling up across the galaxy, and the scaling assumptions carry large uncertainty. Nobody has counted trillions of anything. The honest statement is narrower. In every young cluster examined with sufficient sensitivity, these objects turn up. And in NGC 1333, they accounted for roughly 10% of the cluster's members, a higher fraction than the standard mass function predicts. Even the conservative version of that is remarkable. It means the galaxy is not mostly stars with planets attached. It is stars, plus an enormous unlit population drifting between them, invisible to almost every instrument ever built. We can only see them at all when they are young, when they still carry the heat of their own formation. CHA 1107-7626 is 1 to 2 million years old, which is why it glows. Give it 1 billion years, and it goes cold, and effectively undetectable by these methods. 620 light-years, 5 to 10 Jupiter masses, 6 billion tons per second, 8 times baseline. We caught one of them, briefly, in the narrow window where it was young enough to shine and active enough to notice. There is a version of this story that touches our own solar system, and I want to handle it carefully, because this is the part that usually gets overstated. Here is the solid ground. Two formation routes for these objects are on the table. 1. They collapse directly out of gas clouds, like very small stars. 2. They form around a star, in a disk, as ordinary giant planets, and then get thrown out. The second route is not speculation about how ejection works. Ejection is standard physics. In a young planetary system, giant planets tug on each other. Those tugs accumulate. If two massive planets pass close enough, one of them can be flung onto an escape trajectory and leave the system permanently. Simulations of early solar system evolution produce this outcome routinely. It is not exotic. It is a common failure mode of building planets in the first place, which means our solar system is a survivor of that process, not an exception to it. There is a long-standing line of research proposing that the early solar system may have contained an additional giant planet, a fifth ice giant, that was ejected during the chaotic rearrangement of the outer planets. I want to be precise. That is a modeling result, not an observation. Nobody has found such an object. Nobody has proved it existed. It is a hypothesis that some simulations favor because it makes the final architecture of the outer solar system easier to reproduce. But the physics behind it is not in dispute. If that ejection happened, the object is out there now. Cold, dark, unlit, drifting somewhere in the galaxy, indistinguishable from the population Webb has been cataloging. And that is the honest connection between CHA 1107, 7626, and Earth. Not danger. The odds of a rogue planet disturbing this solar system are vanishingly small. Interstellar space is empty on a scale that is genuinely hard to convey. The connection is origin. The same process that built the ground you are standing on also throws worlds away, and it appears to have done so, everywhere, constantly, for the entire history of the galaxy. What remains unexplained? What fraction of the trillions belong to each root? Formed alone or exiled? Right now the evidence points both ways at once. The mass floor in NGC 1333 argues for direct formation, and the Jumbio pairs argue against simple ejection. Researchers cannot yet separate the two populations. So what happens next? Two things are already scheduled. The first is more of this. The burst was still ongoing when the observing campaign ended at the end of August 2025. Nobody knows how long it ran, or whether it has stopped. And because the archives suggest a similar event around 2016, there is a real possibility that these bursts recur on a timescale of years. That makes CHA 1107-7626 a target rather than a result. It will be watched. The second is a change in the instrument. NASA's Nancy Grace Roman Space Telescope is being prepared for launch, currently targeted for around May 2027. Roman does something Webb cannot. It surveys enormous patches of sky repeatedly, looking for gravitational microlensing, the brief, characteristic brightening that happens when an unseen mass drifts in front of a background star and bends its light. Microlensing does not care whether an object glows. It works on cold, old, dark rogue planets just as well as young hot ones. The mission team's projections suggest Roman could detect hundreds of free-floating planets, potentially down to masses as small as Mars. That is the shift. Right now we can only see the newborns. Roman is designed to find the ones that went dark. And CHA 1107-7626 will keep going regardless. It will finish this burst, or it already has, 620 years ago. It will consume what is left of its disk. It will cool. It will stop glowing in the infrared, and the instruments that found it will no longer be able to find it. There is nothing to stop it, no star to orbit, no system to belong to, no fusion to ignite, and no company to keep. It falls through the Chamaeleon complex, and then out of it, and then through the galaxy, for as long as the galaxy lasts. So what does all of this actually add up to? One starless world, 620 light-years out, 5 to 10 Jupiter masses, 6 billion tons a second, 8 times its own quiet rate. A planet that never had a sun, growing the way suns grow. The title of this video says it shouldn't exist. That's not quite right, and I'd rather be accurate than dramatic. It exists. What shouldn't exist is our confidence that we knew where planets end and stars begin. And if the estimates are anywhere close, if there really are trillions of these objects drifting between the stars of this galaxy, unlit, uncounted, and until very recently undetectable, then this one is not the exception. It is the single example we happen to be looking at when it did something loud enough to notice. It is genuinely worth wondering what the other trillion are doing. If you want more of these, subscribe and turn on notifications. Everything here is grounded in real published research, rather than exaggerated headlines.